Hello everyone. So sorry for the long wait between uploads, but I've been pretty busy over the past few weeks. Today we're going to be talking about tangent planes. So the idea of a tangent plane is, let's take some multivariable graph. Well, actually, let's first look at two dimensions. So if we take some xy coordinate plane and we look at some random curve here, let's call this y equals f of x. And then the idea that we all learned about in single variable calculus was that if we took the derivative at this point, let's say x naught, y naught, it would be the instantaneous rate of change here, the instantaneous slope. And we learned about how to actually define a line that actually has a slope and essentially goes through this point. And the idea with tangent planes is essentially analogous to this, but in multivariable functions. So instead of lines, we have planes because there are infinitely many lines that pass through a point on a surface. So let's consider some multivariable graph. And a nice one that I usually like to draw, which is because it's kind of simple to draw, is basically y equals or z equals x squared plus y squared, because it's, or some variation of that. So we have some kind of, it has a single critical point in the middle, and its concavity never really changes. Oh, that's pretty horrible. Yeah, I thought this was going to be easy to draw, but I guess it isn't. I'll try one more time. So I guess we could do something like, yeah, okay, that's good enough. Okay, so let's think about this graph here. And we just want to get an idea of what a tangent plane is. So if we take some point on this graph here, let's say x naught, y naught, and let's say this function is f, and the z coordinate is going to be f of x naught, y naught. So this is our point, right? And the idea of a tangent plane is that we want a plane that gives a linear approximation of this graph. Now we use the term linear a bit loosely here, because this doesn't necessarily go through the origin as we want. And that's actually lines that go through the origin are linear, and lines that don't go through the origin are called affine. So there's actually a fine line between those. So we're getting, this is the idea of a tangent plane. We want to go right through this point, and we want the partial derivatives at that point in both the x and y direction to match. Right? So let's try to get an idea of this. So let's call our tangent plane z, right? So this is going to be our tangent plane. And what are the properties of z? Well, we need z of x naught, y naught to be equal to f of x naught, y naught, right? And we also need the partial derivative of z with respect to x to be equal to the partial with respect to f with respect to x. And both of these evaluated at x naught, y naught. And similarly, partial z, partial y has to equal partial f, partial y. Okay, so let's try to prove a form that works with this. So let's consider the two lines that pass through this point as such. So we get these two lines by slicing through this point with a plane that's parallel to the x-axis and y-axis. These will give us the definitions of our partial derivatives. So if we consider some kind of plane that slices parallel to the y-axis, well, if it's parallel to the y-axis, then y is changing and x is held constant. So in other words, if we have some line that goes like this, let's say, then the line will have slope partial f partial x, partial y, right? And it'll go through the point f of x, y. And if we take some arbitrary point on this line y, and then we'll need the if we take the distance between the point y and y naught, and we scale it by the slope and add it to the point, then we'll get our line, our equation for a line. So we'll call this line L2. So let's write L2 is equal to, well, so we start at the point x naught, f of x naught, y naught, and we add to that, well, I'll write it as partial, well, with respect to y, partial with respect to y, partial left with respect to y, at x naught, y naught, right? So that's the slope, and then we basically have the distance between basically delta x, right? X minus x naught, because we want to remain on this line. Okay. So now, well, let's define the other line, which whose slope is represented with partial f, partial x. So that will be, let's see, this plane, right? So it'll be this line here, kind of. Sorry for my messy drawing, but we'll call that L1, and that's also going to start with f of x naught, y naught. But this time we're going to have a slope of the partial derivative of f evaluated at x naught, y naught. And similarly, we'll have our delta y. Okay, so now what we want to do in order to get like a plane which goes through this point is to actually find a normal vector to, like, let's say vectors on these two lines. So we want to find one vector that's parallel to this line and one vector that's parallel to this line. So let's first look at this. So notice that this takes place, the motion here takes place in the xz plane. So in other words, we want to find, well, our goal is, which I just said, is to find some vector, I'll call it v1, such that v1 is parallel to L. So, yeah, xz plane. Okay, so, well, our y is held constant, so we'll just let that be 0. So we'll have v1 is equal to something, but we'll have a 0 here. And now we want our slope to be exactly the partial derivative of f with respect to x. So, in other words, let's just take 1 here, and we'll take the partial derivative of x evaluated at x naught, y naught here. Such that, if you think about 2D vectors, if we take this value over this value, we'll get our desired slope, right? Because we're working in the xz plane. Now, similarly, we'll have that v2. In this case, we're holding x constant, so we have a 0 and a 1 and a partial with respect to y at x naught, y naught. So now, actually, let's just take the cross product of these two vectors. As we know, the cross product will be normal to both of these vectors, giving us a tangent plane whenever we take the dot product with basically any point on that plane, or any vector on that plane, I should say. So let's see. So we're gonna have okay. So if we take a cross product, we'll get f1 the first vector crossed with the second vector is equal to the magnitude of the matrix I hat, j hat, k hat, and then we'll have 1, 0, fx evaluated at x naught, y naught, and then 0, 1 evaluated f sub y, x naught, y naught. And we can quickly evaluate this in our heads. Well, here we're going to take I hat times the determinant of this 2x2 matrix, right? Which is going to be 0 times f sub y minus f sub x. So we're just going to get all abbreviated as the partial derivative of f. We'll just leave that evaluated at x naught, y naught out for a little bit. Minus, we can't forget the minus, j hat times, let's see, we'll have f sub y. And then finally we'll get plus k hat, right? Okay. And now just to clean things up a little bit, we can scale this vector by any constant, right? Since that won't change whether it's orthogonal to our two vectors here. So let's just scale this by -1 and get something a bit nicer. So that'll give us the following vector. We'll get the partial derivative with respect of f with respect to x evaluated at x naught, y naught. We'll have partial derivative of y evaluated at x naught, y naught, and we'll have just -1. Okay, so now if we take the dot product of this value with any value here, with any other vector on the plane, then we'll get our equation of our plane, right? Okay. So in other words, well, we can, for example, just if we take, let's just, for example, well, in this case, we'll take this vector dotted with, like, in the general case, we'll have we'll call it the vector x, some xyz on the plane, and subtracted from our x naught, y naught, and then f of x naught, y naught. So if we take the dot product of this with that, we have to get 0 by definition. So we'll get f sub x, f sub y, -1. Again, I'm abbreviating. And then we'll have x minus x naught, y minus y naught, z minus z naught equals 0. So expanding this out, we just get that partial derivative with respect to x. Oh, you can't see that. I should raise the board a bit. Hopefully you can see that. Okay. So partial derivative with respect to x at x naught, y naught of x minus x naught plus partial derivative with respect to y at x naught, y naught times y minus y naught. And then here, well, we can think about this as, well, we'll get a negative z, but we can add that to the other side to get z. So this is actually all equal to z. And then we'll just get a plus f of x naught, y naught. Right? Because our z naught is just defined to be f of x naught, y naught. So actually, this finishes our definition of a tangent plane. So in summary, what we have is f of x naught, y naught plus this term here, which gives us the partial derivative with respect to y information. Then we have this term here, which gives us the partial derivative with respect to x information. And some intuition about just directly applying, remembering this is that, notice that if we plug in xy equals x naught, y naught, then we'll actually get exactly f of x, x naught, y naught. So that satisfies that condition. And, well, you can check that. And actually, another way of kind of proving this in a little less rigorous way is actually considering our z directly being equal to some ax plus by plus c, right? And we want that the partial derivative of z with respect to, and actually you can rewrite this a bit as defining a new constant, capital C. So we'll have z equals, well, we'll have like a x minus x naught plus b y minus y naught plus our capital C. So we can define it this way directly, because notice that, well, if we've notice that we define capital C to basically be just because these are just constants here, so we're basically defining a new constant that considers all of these constants, right? So then, well, actually we find that C is actually equal to f of x naught, why not? And then if you take the partial derivative with respect to x and y of this function here, then you'll actually be able to compute the constants to actually be just, well, what we found here. So although this is a bit less rigorous, it still works quite well. And maybe if you forget it, this might be a better way of finding it again. Okay, so that is it for the video. I hope you enjoyed, and I'll see you in the next video. I actually might be making a video on quadratic approximation, but I'm also planning on making a physics video and continuing the calculus series. So have a nice day. Goodbye.